Imagine trying to predict how a system will behave. If the system is integrable, that means we can solve it exactly and understand its global behaviour. But many systems are just too complicated for traditional tools like integration. In the 1980s, a mathematician named Zyglim made a breakthrough. He connected the idea of monodromy, how solutions twist around complex paths, to whether a system could be solved. In the 1990s, this was extended by Morales, Ramis, and Simo, who linked solvability to Galois groups, which are deep structures from algebra. My research follows this framework. I study a class of dynamical systems called Hamiltonian systems, specifically one known as the Friedmann-Robertson-Walker model, which is a quartic Hamiltonian system. This is used to describe an expanding universe, like the one we live in. The first numerical tool when looking at solvability is to produce a Poincare section, and these bottom graphs are an example of exactly that, where the closed curves represent integrability and the regions with dots represent chaos. Following this, the method I am using involves complex time paths and calculating a monodromy matrix, so time can move in any direction on a two-dimensional plane. These are produced from variational equations, which study tiny perturbations in the system. If the system is integrable, these matrices will commute. But when they don't commute, it's evidence that the system is not integrable. That is exactly what these graphs on the right show. If the matrices commuted, all we would see on the graphs is a straight line on the horizontal axis, but this isn't the case. The vertical axis on both of these graphs are the infinity norm of the commutator, that is, the largest value of the matrix by row. The top one, case 1, is for when the two parameters of the system, the gravitational field strength and the self-coupling of the scalar field, are defined in terms of the mass. We see exponential growth, which is numerical non-integrability evidence. The bottom graph is for cases 2, 3 and 4, where the parameters have their own formulas with p as a variable. We also see non-integrability evidence as the curves are nearly always not equal to 0. This numerical evidence leads us one step closer to fully understanding the Friedmann-Robertson-Walker model, and for which parameter values non-integrability will occur.